Let's now determine the Lewis dot structure and the electronic and molecular geometries and determine the polarity for nitrite ion. And the approach we're going to take is to first determine what we call a NASA table, and from that we'll make a Lewis dot structure. Then we'll determine the electronic geometry, and from that we'll determine the molecular geometry, and then from that we will determine if the material is polar or not. And so with that, let's begin. The first thing we will do is make out our so-called NASA table. The needs line: my one nitrogen needs 8, and each of my 2 oxygens needs 8 electrons, for a total of 24 electrons. As far as electrons available, my one nitrogen brings 5 valence electrons. It's in group 5. And each of the 2 oxygens brings 6 electrons. They're in group 6. And we also have 1 extra electron that's giving an overall negative charge. So we'll add 1 for that and bring the total number to 18. 24 minus 18 is 6. Therefore, we have 3 bonding pairs. Okay, and that is our shared line. And finally, what we have additional or left over is going to be 18 minus 6, which gives us 12 electrons, or a total of 6 lone pairs. And so let's use this information to make a Lewis dot structure. We see that nitrogen is going to be our central atom. Single bond that oxygen. And now let's place our 3 bonding pairs. We have 2. Let's now place a 3rd one. And let's place our 6 lone pairs. Remember, place them on the pendant group or outer groups first. And anything that's left over, we're going to place on the central atom. So this oxygen has 1, 2, 3, 4, 5, 6, 7, 8. We stop because we said oxygen needs 8. This oxygen has 1, 2, 3, 4, 5, 6, 7, 8. We'll stop there. And I see a total of 5 lone pairs has been placed. So I need to place 1 more. So it has to go on the central atom. This is the Lewis dot structure. I'm going to put it in brackets with a negative sign to remind us that that is negative. Let's now determine the electronic geometry, and to do that we merely count the areas of high electron density, which you recall is the number of single bonds plus the number of double bonds plus the number of triple bonds plus the number of lone pairs. And so let's count them. About the central atom, I see 1 single bond. I see 1 double bond. I see no triple bonds, and I see 1 lone pair. So I have a total of 3 areas of high electron density. Therefore, the electronic geometry is going to be trigonal planar. Now, to determine the molecular geometry, we want to use the electronic geometry framework and flesh it out using our Lewis dot structure. The central atom has 1 oxygen connected to it. It has a 2nd oxygen, which is double bonded, and it has a lone pair. Those are our 3 areas of high electron density. Now, to get the molecular geometry, you merely hide the lone pairs. And what we're left with is a shape that looks like this. And so we recognize that as bent. And we also see that because it comes from a trigonal planar framework, which is 120 degree angles, this too is 120 degrees. So we would call this a bent 120. And I'm going to test for non-polarity, as it were. And so what are our checks for non-polarity? The 2 questions are, 1, does it have the same pendant group? And remember, we define pendant group as these groups which are attached to the central atom. And, it's very important, this is and not are. And does it have symmetry? A compound is said to have symmetry if its molecular geometry is equal to one of the electronic geometries. And in this intro class, we've only covered 3 types of geometries: linear, trigonal planar, and tetrahedral. And as you can see, this is bent. It is not one of those 3, so it fails the symmetry test, although it does have the same end groups, and it passed the end group test. So because one of them failed, we conclude that this material is in fact polar. In summary, nitrite ion has this Lewis dot structure. In 3-dimensional space, it is bent at a 120 angle between the bonds with the oxygen, and that ion is polar.